Picking up from where we left off in part 1 here, you can see in red I've scribbled a few things down here in the way of talking about what this pKa is all about. These numbers for pKa measure the tendency of one to be able to remove the hydrogens from any of these hydrocarbons, removing the hydrogen in the form of a hydrogen ion with a positive charge, which would create a carbon with a negative charge, which in turn is a very reactive type of thing. So one of the ways in which we look at organic compounds and assess what kind of reactions they can undergo is to compare them in terms of their hydrogens and how easily they can be removed as hydrogen ions. pKa is a scale of numbers that does that. If you recall, Ka itself, the acid ionization constant, is defined this way. If Ha is a general acid, then again we're talking about removing hydrogen with a positive charge, making essentially a proton, and then leaving behind a negatively charged anion, which I guess is what the A stands for. And so Ka involves the concentrations, the molarities of the two ions divided by the concentration of the unionized acid on the bottom. So the bigger the value for Ka, the stronger the acid, the more it produces hydrogen ions. And Ka can cover a number of powers of 10. It can be anything from 10 to the negative 60 to 10 to the positive 10 or positive 11. So it involves an enormous range of values. So that's why the pKa was invented. Similar to pH, it means you're taking the negative logarithm of Ka. And so for most substances, that gives them positive values that vary from 1 or 2 up to, as you can see on this slide, 45, 62. And so it's a way to compare molecules. And the point of this is that compared to alkanes like ethane and alkenes like ethene, carbon-carbon triple bond molecules, the ethine here, is enormously more acidic. Not such that you would get much hydrogen ion if you just put it in water, but compared to these other hydrocarbons, it's enormously more acidic. The difference between 45 and 26 is 19 units. So that's a difference in acid strength of 10 to the 19. So that's telling us that this ethine is enormously more acidic than either of these other two. This kind of refers back to this table from your book. If I can get that to stay up here. This thing is table 1.8, so it's way back in the first chapter of the book, and it has pKa for a whole bunch of substances. Things that we normally think of as strong acids, notice they have negative pKa's. They're at the top of this list. Things like sulfuric acid, which is battery acid, hydrogen chloride in your stomach, we call that stomach acid. And so that implies that their values of Ka are quite enormous. And as you look down through this list, they just really show a lot of things that are common in organic chemistry, and they've listed them in order of pKa. Again, the lower values are stronger acids. Here's acetic acid. That's what's in vinegar. Typically has a pH of about 2 or 3, and so its pKa here 4.7. So not so strong that it's something you can't ingest, but certainly a lot stronger than things that would have a higher value of pKa. And so this is a rather comprehensive list. In fact, it continues on to another slide here, and this is the very bottom of that list. You can see they've got methane down here, value of 60, and ethane 62. I can't quite get that one in the frame there. But for substances that have only carbon and hydrogen, their hydrogens are very difficult to remove, very, very weak acids. But in this list, they also have acetylene here with a pKa of 26. So again, it's somewhere in the middle between the things that are the weakest of acids and the substances that are thought of as being relatively strong acids. And so what that leads into is this next slide. That means if we take a acetylene or ethine molecule and expose it to a strong enough base, then we can remove one of these hydrogens. Now in this first equilibrium, well, it's telling you hydroxide doesn't do this very well. These arrows are drawn to imply that this equilibrium lies very far to the left, so you don't get a whole lot of this negative ion. That thing is called an acetylide ion. It's the negative ion of acetylene. And in fact, any alkyne that exists as its negative ion, they're collectively known as acetylides. So we can make these if we use a strong enough base, and we'll see in this chapter this NH2 called amide. It's related to ammonia, but with a negative charge it becomes amide, and it is something that's fairly cheap and easy to come by, and it's very good at removing the hydrogen from acetylene compounds. And you can see that's what's being shown here. If this hydrogen were attached to a carbon that had a double bond or a single bond, this would not happen. But amide is just a stronger version of hydroxide, and you can see this equilibrium does lie towards products. And so if we can do this, if we can create this carbanion, this carbon with a negative charge, it becomes a very good nucleophile, and it can engage in a lot of interesting reactions. And compared to, again, alkanes and alkenes, these alkynes have this going for them. They are just barely strong enough as acids that we can engage them in reactions that does create these acetylide ions.